stability, you just can say that stability of the standard solution or sample solution. Yes, that forms part of the MPC. Okay. Sensitivities, yes. Sensitivities, yes. And we have touched on the big topic on calibration. Yes, calibration is relatively a big topic because without the calibration, no matter type 1, type 2, or type 3, the traceability is established. While the calibration, either to SI unit or comparison of your signal with the CRM or material, which is then traceable to the CRM, okay? So for calibration curve, we have type 1, type 2, type 3, and we also have within batch and fixed calibration, just different classification, okay? And last week we come to another type of classification, that is mainly internal standardization, external standardization, and standard addition, okay? So for internal standardization, there are two types. One is addition of surrogate. Surrogate is added to your sample solution before mark up to the volume. So it haven't gone through the whole extraction process. Its main function is to correct the drift in your instrument. Correct the drift in the instrument. And for surrogate, both of them are similar to your analyte, having similar retention time, may not be exactly the same. The most ideal internal standard or surrogate is the analyzed isotopic analog, okay? Because the behavior will be totally the same, except the molecular mass. So for surrogate, basically, it is added to your sample before going through the whole process. That means your surrogate and the analyte are extracted from the very start beginning. And you can't assume that we can totally get back what we added to your sample. So by loss of your surrogate, you can correct also the loss of your analyte. So that is the idea. So if we use surrogate for the internal standardization, we have corrected recovery. The recovery is always quite high. So even though when we say we are conducting trace analyte down to BBB level, but still we can get high recovery up to 80 to 100 and something percentage because the recovery is corrected, okay? Don't think that we can totally recover all our analyte from our sample. There will be loss to your gasware, loss to your cleanup process, or loss in the solvent extraction, because solvent extraction just depends on the coefficient of partition. It is not 100% for most of the case, okay? So the most, you should say, quite completely digestion process is digestion of elements. That is quite approaching to 100, but not 100. Normally we can't get 100%, okay? So when somebody say that, oh, your method is so worse, it is not 100%. In such a case, just demonstrate the one who asked you the question is a non-practitioner. He doesn't have any experience, practical experience on laboratory operation, okay? This is the same. When I work in the government laboratory, my boss also say that the recovery is not so good, just 80-something%. but I'm detecting 0. something ppb level. So just a reflection of the discipline you are working in. When we go to specific discipline, you will understand the requirement of different discipline is totally different. So when somebody works in the pharmaceutical sector, he will say that you fail the test if the recovery is so low, lower than 95%. The concept is totally different. It all depends your objective, the concentration, the target analyte. Okay? So when we talk about type 2 and type 3, type 1 is traceability by physical constant to SI unit, normally, either to temperature, to kg, or volume, which is indirect to kg, okay? And type 2 is comparison of signal of your sample solution with that of a pure solution. Type 3 we call matrix calibration. In such a case, the signal will be largely affected by the matrix. Typical example is MSMS type analysis, because that is not a complete ionization process. We try to keep the energy low to capture our parent's ion, not to break down the parent's ion. So the energy relatively is not so high as the GCMS, we call soft ionization. By capturing that, we go to the second quarter, at which collision of inner gas with your captured ion will be occur. Then it will break down into your daughter ion, okay? So this is known as quadruple. Now, another type of matrix matching. Here I show you that is a elemental analysis. You just say that elemental analysis is quite complete. When we use acid to digest our sample, all the elemental compounds will be soluble in nitric acid. Okay? So the matrix form is quite similar. Why is that you still need to matching the matrix? I'm saying matrix, not matching the solvent. Last week I told you that somehow you may need to match the solvent blend with your calibration blend, or your calibration blend with the solvent blend, because of the viscosity. So when we digest our plastic with concentrated sulfuric acid, the density of sulfuric acid is higher than that of the nitric acid, and we use 10%. We use concentrated nitric acid to digest your plastic. The resultant sulfuric acid is around 10%, okay? And the viscosity will be much higher than your 2 or 3% nitric acid. In such a case, the signal response will not be the same. So it all depends on your instrument. If the instrument is good enough and your pipeline, your pump is large enough, then it will not have any difference, okay? The total mass entering in the ICP OES will be the same. But if the pipeline is quite narrow, it will be affected by the viscosity. So I can't say that you must need to match the calibration blend with the solvent blend. It all depends on the instrument. You need to check. Now for this example, we need to prepare our sample solution. We need to prepare our standard solution in the matrix of the sample. Why? Although this is a elemental analysis, the reason is the sample itself contain lots of interference affecting the determination of your analyte. Okay? So let's see an example here. Determination of lead in steel or iron by ICP-OES. So for steel or iron, it is metals. When you use corn nitric acid to digest it, it will be totally dissolved, because steel or iron contain metals, okay? But for steel or iron, I should say for iron. For steel, it depends what type of steel. For stainless steel, the amount of iron will not go up to 95%, but somewhere around 18 only, okay? Because it contains high concentration of nickel and chromium. But for steel, or the carbon steel we say, used for construction to build up the building, the amount of iron is around 95%. It's around 95%. Don't think that ICP-OES is very confirmative. For any element, the emission spectrum is not a unique wavelength. It has many wavelengths that it can give out energy. That means it can have emission light. Understand? But just that the coefficient of emission, you can say, is not high enough for quantitative analysis. But you see the difference. For example, if we use 0.5 gram of iron, digestion with nitric acid, and mark up to 100 ml with water, okay? What is the concentration of iron in the sample solution? 95%. This is very high. 95%, the dilution factor is only 200 times. Because 0.5 gram to 100 ml. So the dilution factor is 200. So the concentration of iron will be 95%. 95%, that means 95 gram per 100 gram. And then you have 0.5 gram times 0.5 gram, okay? 0.5. And finally, it dissolves in 0.1 liter. So the final is 4750 mg per liter, because we still need to multiply by 100, and this will be mg, okay? So here, so no decimal place, this will give you 4750 mg per liter. That means 0.5 gram. We have 0.5 gram. And the percentage will be 0.95. That is in gram. And we turn to mg, multiplied by 1000. And then the volume is 100 ml. That corresponds to 0.1 liter. The concentration will be 4750 mg per liter. So this is very high. The concentration is very high for ICP-MS. All the signal will be saturated if this is the quantitative wavelength. So assume, just assumption. We need to check. Of course, we need to check. We want to determine lead in steel. Assuming emission of lead at 220. 220 is the typical emission wavelength for lead. It's around 400. Just an assumption, give you, because this emission coefficient will depend on your instrument, okay? So if this is 400, and emission of iron at 220 is 0.04. Iron, the wavelength, the optimum emission wavelength is not 220. It's other wavelength, 200 something, I can't remember, okay? But at 220, or maybe somewhere around 220, it also have emission. The quantity is 0.04 per mg per liter, okay? So this is the pure lead standard solution, 0.5124, and this is the signal, okay? And this is the lead in iron solution. What is the meaning, lead in iron solution? We prepare the lead, we add the lead standard solution to pure iron solution, to correct for the contribution of signal from the iron, okay? Because in your sample solution, you always have 95% of iron. So in your standard solution, we also add 95% of iron to match the signal difference, So if this is the assumption, the signal of iron contribute by 4750 mg per liter will give you 190 signal. The count will be 190. Just using the emission coefficient multiplied by the concentration will give you 190, okay? And the original signal of the acid is 12. These two make up together will be somewhere around 205 or 202, but just some fluctuation. That means the band signal plus the contribution from your iron, okay? So this, the second, then the contribution of lead will be higher, 200, but still you have the contribution from the iron. The two make up together is around 400, and this even better, okay? 200 plus 400 will give you 600 something. So now this time we have a calibration curve constructed from pure iron, and then we have a calibration curve constructed from pure, this is pure lead. This is pure lead in 95% iron solution, okay? So the slope basically is more or less the same. The slope is the same because this is proportional to the lead concentration. So the slope will not be changed largely, but only the intercept will change, because this intercept is basically the background of your iron solution, okay? So the coefficient, both of the equations are quite good. Now, if we have a, what is this tool? Oh, maybe just, no. This is some, I should delete this. Now, given a sample solution, iron solution, this sample solution contains 95% of iron. The signal is 850. If we use the pure lead standard solution calibration curve to quantify the result, then the concentration found in the sample solution will be 2.1 mg per liter. But if we use the matrix calibration curve, then the lead concentration will only be 1.6. See the difference? The deviation is around 30-something%, okay? That means if you compare the signal of your sample solution with a pure standard solution making up with lead, you will overcount or overestimate the concentration because you haven't correct for the contribution of iron in the sample solution. Okay, so this is a matrix calibration curve. We match the matrix of our calibration curve with that of our sample to correct for any contribution from the sample. But in such a case, all the sample should be relatively be of similar matrix. Otherwise, sometimes you will overcorrect it and sometimes you will be undercorrected. Okay? So if the contribution of iron is very serious, affecting the result, then for different type of steel, you need to prepare different matrix calibration curve, okay? Because the amount of iron in different types of steel are quite different. So this is matrix calibration. So, any questions up to here before we move on to another MPC? So we spent more than one lessons on the calibration curve. And this is a mandatory questions in the examination or in the laboratory report. Yeah, you need to construct calibration curve and to comment on the calibration curve. What is the meaning on comment the calibration curve? Comment on the calibration curve is something like that. Something like this. I give you some signal, either with internal standard or without internal standard. If I give you internal standard, always put the ratio of signal of your analyte over the internal standard, the ratio against the concentration. Don't put the absolute response, okay? So something like that will happen in the examination. I give you a table, then you need to calculate the X deviation, the residual, the slope, the coefficient of variance, and also the intercept. And based on this, you will comment whether this calibration curve fit the intended use. When I say fit the intended use, of course, I give you some description of the intended use. For example, how many grams of sample, then dilute up to maybe a certain volume, and then add up the internal standard and anything else. Then the questions come, the range, whether it cover the lowest reporting limit. That is, you need to check. The second is whether this is a linear plot, whether there is large deviation, or whether there is saturation. So may not be rejection of the lowest point, may be rejection of the highest point, I don't know, okay? That is how to comment, and whether the calibration range is good enough. If I set a calibration curve from 0.01 to 10 ppm, can you say that this is a good estimation? 0.01 to 10, that is 1,000 free order. There is no instrument. The linearity can cover so large without good correlation. Okay? So that is how you comment on the calibration curve. And also whether the spacing of the calibration curve is good enough. Okay? That are all sorts of points you need to give to me to fit the intended use, and aware of the dilution factor. always, okay? So, some sorts of this. And before exam, you can always prepare a table first. But we will take examination in the computer room. And before break, I will ask you whether you want to postpone the examination 1 week after the term break. That means after the last lessons. The last lesson should be around when? I'm not sure. Should be 15. But that week, you have 2 examinations already for quite a number of you, isn't that? And on the 6th to 10th, you have another examination. So, if I insert the examination on the last week, it may be too heavy for you. So I can postpone 1 week to 22nd. But some of you may need to go back to hometown. I'm not sure. If there is nobody there to hurry back to your hometown, then we will have the examination to be conducted on 22nd. It may not be on 22nd, any day the following week, okay? Because you have aimed all the other lessons already. So the examination can be on 20, 21, 22nd. So it's up to you. Up to you. Don't delay too much because I need to mark up your examination paper and return everything to the admin. So think about it first. Yes? If you want to hurry back to the hometown, then we can take the examination maybe on 20. Then you can just go back to hometown on 21. Okay? So after the break time, make up your mind. Make up your mind. Okay? No questions? Then we will go to another topic. So this is just the extract from the Excel file, nothing new. So the most of the common mistake we encounter for calibration curve, it doesn't cover the sample concentration at the reporting limit. And then the concentration of calibration standard not evenly spaced across the calibration range. Calibration standard not properly prepared. That means from 1000 ppm stock solution directly go to PPB level using micropipette 1 microliter. How can you say that 1 microliter is very accurate? So that is improper. You need to have an intermediate if the concentration is too low, okay? So for one of the assessment I go to, yes, I ask them, where is your stock? 1000. Then what concentration is your intermediate? We don't have any intermediate. And their standard solution, I think, should be somewhere from 0.5 to maybe 10 mg per liter. Then I ask them, how do you prepare 0.5 directly from 1000? The final volume, assuming 100 ml. 100 ml times 0.5 is equal to V times 1000. V is equals to 50 over 1000. Then 0.05 mil, that is 50 microliter. 50 microliter is still achievable. But if this is 0.1 ppm, that means you need to withdraw only 10 microliter. Then this is quite inaccurate, I should say. Quite inaccurate. And unluckily, I found out that their result in the PT is always a negative bias. For 2 to 3 times, their result in proficiency testing program, although still acceptable, that means the EZ score is within 2, but it is always lower than the other laboratory. That means negative something. That we say negative bias. That means there is something wrong with their process. This may due to the calibration curve. If the calibration curve is wrongly constructed, the volume is not so accurate. It will affect the slope. So everything may be overestimate or underestimate. We don't know whether the volume is over volume or under volume. We don't know. Okay. So this is improper. We say that. And calibration falls full 0. Normally, when we plot a calibration curve, we have the 0 point. We count the 0 as the 0. But there will be an intercept. Because for your calibration blank, you still have some contribution to the signal. Whether this is electronic noise or this is impurity in your calibration blank. Still remember when we talk about acid, for different types of acid, the amount of impurity can range from PPT to PPB and then to ppm. So it all depends on what calibration brand you use. It may contribute a background signal. So then for some laboratory, they just neglect that point and force full 0. That means, what is the meaning of forcing full 0? Example, the 0 point basically should be here. And then forcing full 0. That is forced 0. 0 will be 0. That means you haven't correct for the intercept. And this will affect both the slope and also the intercept. And the effect will be much more serious at low concentration. Okay? So don't think about by yourself. Don't just take all the advice from the engineer. They are not analytical chemists. They are engineers only. So somehow the engineer will say that just select the forcing full 0 button, then it will be good. Our instruments are very strong. Yes, their instruments are strong, but the application is different for different laboratory. So think about your intended use before setting any figures. Normally we just take linear and then using the 0 point also as one of the calibration standard. So performance of equipment not within specification, no sensitivity or calibration range. That means they haven't checked, imposed any quality control check against the daily performance of the instrument, especially for internal standardization. It is quite dangerous. It is quite dangerous for internal standardization. You can always have proper ratio of your midpoint solution, but not sufficient good at the lowest point if you use fixed calibration. Okay? And we will talk about this when we go to the QC part as a QC parameter. What's the meaning of instrument software calibration not checked? This is a funny case. Also observe when I go for assessment. That is a AA analysis, atomic absorption analysis. No matter graphite or flame. So normally you will have the pinout including the calibration curve. Okay? And within the calibration curve, it is very small. And including the zero, there are 4 points. So I can see a more or less like that, similar to a straight line. And then they calculate the linearity. Because the instrument doesn't give out the linearity, but the laboratory themselves, they calculate the linearity using the coefficient of variance, okay? And then the result directly out. Directly out from the instrument. When I check upon the setting, this is a rational port. Instead of linear port. What is rational port? This is also the advice from the engineer. For rational port, that means there are many different types of port. You have they just smooth out this. Smooth out using quadratic port. So when I see from the screen, the port is much larger, then I can see that this is not a linear port. Although when they carry out the linearity, it still sounds to be linear, but not linear, okay? So they join the point by smoothing around. So this is a curve instead of a straight line. And when you fit in the signal, when I calculate back, there are a few percentage deviation. That means the readout from the instrument is quite different from the linear graph by manual calculation. Yes, I should say the difference is not so big, a few percent, 3% only, 3 to 4%. But this is the principle. You don't understand what you are getting. So do have a look on your menu, the different types of port. The meaning is quite different. For ICP, OES, ICP-MS, AAS, there are different selection of your calibration curve. Do have a look first before moving on, okay? So this is an interesting case for AA. And I asked them, what is this port? Oh, the engineer say that this is good. So I just copy that. But they don't understand what is the rational port, okay? Oh, these are all sorts of reference on calibration curve. I have given to you the first one, VAN. And basically all the material on calibration are mainly extracted from this reference. Limits. What are all these terms? So many L. LOR, PQL, LOQ, MDL, IDL, LOD, LLD. So I give you the full name of this so-called L or limits. Instrumental detection limit, limit of detection, lower level of detection, method detection limit, practical quantification limit, limit of quantification, limit of reporting. Normally, we have such all sorts of limits. And which limit do we need to determine for our method? It all depends on the discipline. For some of the limits, we don't need that. But for some of the limits, it is specified in the standard. You need that, okay? So, as a general, we have IDL, if this is an instrument. We have LOD and LOQ, and also LOR, that is reporting limit. These four are the fundamental limits for a quantification technique. For qualitative technique, we don't need LOQ because we don't need to quantify it, okay? So that is not necessary. Now, we will see how to establish this limit and what is the definition. LOD and LOQ. It is defined for a method. You need to clear your mind or make it clear. When we say a method-related limit and a limit related to the instrument, that is different, okay? So LOD and LOQ are related to a method. Defined for method intended to measure analyte at concentration close to zero. Even for a single method, the LOD and LOQ may be different for different matrix because the background interference will be different. Okay? So, how far can you differentiate the signal from the analyte from that of the background will affect your LOD and LOQ. And when we say LOD, basically it contains two components. One is the MDL, another one is the IDL. MDL is the method detection limit. IDL is the instrumental detection limit. Okay? So, it is quite easy to determine the IDL. IDL is the lowest concentration of analyte that can be detected or differentiated from the background using a given measuring instrument or detector. Okay? That means significantly that is a signal different from your background. Then that is the IDL. But how to define this is significantly different from the background? It all depends on your need. Normally, for some of the analytical application, we will define a signal to noise ratio of 3. Then we can say that okay, this should be a signal from the analyte, not the background. Okay. Somehow, if there is no instrument that can fit the intended use, then we can optimize the condition to use an SMASO of only 2. Then we say that, oh, that should be signal from the analyte, okay? But of course, if you use a signal ratio to be 2, that means you will have lots of false positive result, okay? So if the sensitivity increase, that means the instrument is very sensitive. The IDL will be decreased. That is better. When the instrument noise decrease, the IDL also decrease. That is natural. because we want to differentiate signal from analyte, of analyte from the background, okay? So what about method detection limit? Method detection limit, according to NATA. NATA is the accreditation body of Australia. Smallest amount of concentration of an analyte that can be readily detected or differentiated from the background for a particular matrix by a specific method. So for MDL, it refers to the method. That means you should go through the whole signal. You should go through the whole process. The background will be much higher than that of the IDL, okay? Because for the IDL, we say that the signal from the analyte, the only interference is your calibration solvent. But for method detection limit, the interference of the background is from all sorts of reagent you use, the glassware, the consumable that have been in contact with your sample during the sample preparation, okay? So there are lots more of reagent and consumable. So normally, the MDL will be higher than the IDL. So this is the difference between MDL and IDL. For LOD, somehow we just say LOD is basically the same meaning as the MDL. Of course, we have integrated the IDL and MDL together and give you the LOD, but in general term, they don't. We will say LOD is basically equal to MDL, okay? But they use in different disciplines. MDL used in environmental testing, LOD used in food testing, pharmaceutical testing. What about consumer products testing? For consumer products testing, sometimes they use MDL, sometimes they use LOD. Different standard use different terms. It is quite difficult for the laboratory. You can't harmonize your terminologies. So maybe you can say that except unless otherwise stated in the standard, you can define your terms as LOD or MDL. It depends on you, okay? The definition, you select one of the guidelines to define all the definition, okay? So what is limit of detection? That is a given procedure. You can measure the probability of false claiming the absence is B, and the probability of false claiming its presence is A. That means the false positive and false negative, the probability is A and B. Don't think that we have 100%. The LOD is just a statistical cutoff. That means at this cutoff, when the signal is larger than this cutoff signal, then any signal you detected is contributed by the analyte. And below the cutoff, you may still have the analyte, but just that the signal is lower than the cutoff. You still say that we don't contain any analyte, okay? So, still remember the two normal distribution. So one side is the false positive, another side is the false negative, okay? So we have probability of B as the false negative, and this is false positive is A, okay? And how to determine the LOD will depends on the probability A and B. A and B. If you allow a higher probability of A and B, then the LOD determined will be lower. If you allow a smaller A and B, then the LOD is higher. Okay? So this, the limit of detection, expressed as the concentration, is the amount of quantity divided from the smallest measure XL, and this defined by this equation. XL is the value of your analyte. Is equals to X blank, that is your blank. We can turn this all into signal. Signal of the lowest concentration at the LOD is equals to the signal of the blank plus K of time the standard deviation of the blank. Okay? This S is standard deviation, this B is blank. So what is K? K will depends on the A and B probability. A and B. We need to check against the T table. And the number of vapor K you use to determine the LOD. Okay? So different guideline will have different A, K. Will have different K. Now, have a look first. That means we target at the linear range for quantification. But below the linear range, you always have a high possibility that the quantified signal, quantified level is uncertain. So at the lower concentration, the signal will be much lower. Then this is the LOD. At a higher concentration, the signal is higher. Then we define as a LOQ. But how to establish this LOD and LOQ? So let's see. So I think I have given to you these figures first. This is another definition as published by ISO 11843. Basically, this is just the same. The true net concentration amount of analyte in the material to be analyzed lead to with a probability 1 minus B that the conclusion, the concentration of the analyte in the analyzed material is larger than that of the blank matrix. That means if we allow 5% error, B will be 0.05. That means above the cutoff, we are certain that there are 95%. That is a positive sample. Not 100%, never 100, only 95%. Okay? So, this is a qualitative look. In sensitive method, is an insensitive method means that there is interference, there is suppression of the signal. Maybe or may not be. If there is interference, yes, the background will be higher, your LOD will be much higher, okay? So in order to reduce the LOD, you need to remove the impurity. That is one approach. Or you need to use a more selective method or sensitive method. So it depends on the situation. It depends on the situation. This is the guideline how to determine the LOD and LOQ. LOD and LOQ are determined simultaneously. We don't need to repeat the test. Replicate measurement of blank sample, matrix containing no detectable analyte, or replicate measurement of test sample with low concentration of analyte for 10 times, okay? and calculate the standard deviation and calculate S naught pi from S naught. That is a flow chart, okay? And the LOD is equal to 3 times S naught pi. Oh, so many S naught. What's the meaning? Really can't understand, okay? For the B case, replicate measurement of reagent blank. Reagent blank here is the process blank. Or replicate measurement of reagent blank spike with low concentration of analyte. We adopt the B approach only when impossible to obtain blank sample or all the sample are positive with high concentration of your analyte. Okay, so we will use procedure blank or reagent blank or low level spike. So the best approach is use matrix blank, that is blank sample, or matrix blank with low concentration of your analyte. The concentration of the analyte is not important. We are just want to study the variation in signal near zero of your analyte for 10 times. Then let's see what is S naught and what is S naught pi. This is the flow chart. So from result of M replicate measurement, then we calculate the standard deviation S naught. Will result be the band corrected during routine use? If yes, then we need to calculate the S naught pi again. If no, we will also calculate the S naught pi. That is equal to S naught over square root n, okay? And use this S naught pi for calculation of the LOD and LOQ. So one very important is the interpretation of n. N is the number of replicate measurement average when reporting result. Where each replicate is obtained following the entire measurement procedure. Normally, for most of the laboratory, when you repeat the measurement for 10, then they will say that n is 10. Is that right? Is that right? By definition, S naught pi should be the same as the real measurement procedure. That is your method procedure. N is the number of replicate you perform for analyzing your sample. Normally, we just analyze the sample for once. Sometimes some standard will say that you need to analyze your sample for twice and then report the mean result. At that case, the n is equal to 2. Okay? And now, if we analyze for 1, then that will be 1. So when you study the LOD, if each time you report average result, then for each time you take 2 measurements and then repeat this for 10 times. That means total 20 data, but take the mean for calculation. Mimicking this is the real sample, okay? Get the meaning? So n here is not 10, but only equals to the number of replicate for your method. If the method, the reported result is based on 1 data, then this is 1. The result is based on duplicate data, then n is equal to 2. So some method, they need to repeat the test in triplicate, then n will be 3. For chemical test, normally n is 1. Okay? So what about, we have M and NB. NB is the number of times of measurement for blank. Also, this is based on your method. For some of the standard or some of your in-house method, they will correct the blank. But normally, we don't correct the blank. The calculation will be totally different. I will give you an example so you will understand more, okay? But first of all, understand the concept of N and NB and what's S0 and SB. So, for your chem, LOD is equal to the mean sample blank value plus 3 times the S0 pi. The sample blank give a non-zero standard deviation, okay? Or 0 plus 3 S0, if the 0, that means the blank, the mean result is 0. But this is quite impossible. This approach assumes that a signal more than 3 times above the sample blank will only have arising from the blank much less than 1% of the time, and therefore is likely to have arising from something else, such as the measurand. That means when the signal is larger than the signal of the mean blank plus 3 times standard deviation of the signal, then the false positive is only 1%. Is only 1%. And the false negative is also 1%. Okay? That means if you have a graphical plot, this is the x of the band, mean band. But every time you measure the band, the signal will not be the same. Okay? So we have SB. SB is standard deviation of blank. How to get SB is x1, xb1, xb2, xb3, xb10, for example. Then we have x bar b and have the standard deviation xb, okay? xb, still remember how to calculate the standard deviation? Using the Excel, and that is xb1 minus x bar b square summation over n minus 1 square root. That is the standard deviation, okay? Showing the variation of each point from the mean value. So again, when you understand normal distribution, we say that this is 3 times the standard deviation. If this is multiple determination, when the 3 standard deviation, that means 99.7. Out of 1,000 measurements, 997 will fall within this range. Is that? But now we just have 10 measurements. The t value will be much bigger. But remember, we look for 1 tail, not 2 tail. Anything larger than this, no need equal to, okay? The scenario is x larger than x pi plus 3sv. This is the scenario. So 1 tail, not 2 tail, okay? So when you go to check the t-table, go for the 1 tail. Of course, when we look at the t-table, if this is 10, that means the degree of freedom is 9. Let's have a look on the t-table. The 3 is just arbitrary. They don't go for the t-table. Let me see whether I have a T table. Oh, I have a statistical table. This is what test. Degree of freedom. This is the T. So here, if 1%, that means 99. 1%. Oh, there is no 0.5. 1%, this is two tail. One tail, you just divided by half, okay? Should be 0.5, but we don't have 0.5 here. Here, 1%, the next one is 0.2, okay? We should check if we go to a two-tail T table, but our target is one tail, then cut the confidence by half, okay? So, you can look at that. For 9, degree of freedom is 9, because 10 replicate. 9, if 1%, that is 3.24. But this is somewhere here. So it should not be 3 as naught, but a little bit, the figures should be larger than 3.3. But this is a general assumption. When you say the mean result plus 3 standard deviation, this is good enough. They make an assumption. So if you look at the T table 3, oh yes, this is 3 here, but 9, 2.82. So it is much better. When we look at the 2%, then that means this is 1%, T1. Yes, 2%, two tail. That means one tail is 1%. So 9, the figure is 2.82. We multiply by 3 already. It's better than the T table, okay? So the assumption is valid. So when we multiply the standard deviation by 3, it is better than 1% error, okay? That is from the T table. When you look at the T table, then this will give you the good answer here, okay? Degree of freedom 9 should be 2.82, but it round to 3. So a little bit more, better than 1%. Get the meaning? Get the meaning? Know how to look at the T table? This is a two tail. If we target at 1%, then look at the 2%. If we target at 5%, then we look at the 10%, okay? And then go for the degree of freedom. Then you can find out. The figures are totally different. So, when we say LOD, this is just an approximation or estimation from the background, a calculated value, okay? So, there is another we call decision limit. This decision limit, CC alpha, will be applied only for food testing. At this level, that means we will take legal action. We will go to the market to collect more samples to determine whether this is really a non-compiled sample. So we set a higher risk factor. That means the alpha will be 5%. The A and B will be 5%, not 1%. Even though there is false positive, we still go to the market and then get the sample and go to the legal government, to the government laboratory, I should say, and they will process with the legal procedure, okay? So how to get this CC alpha? Everything is just statistic. CC alpha or CC beta, one side is the false negative, another side is the false positive. So it multiply a figures of 1.64. 1.64. That means this is 3 standard deviation. Now they cut off the signal more or less around here. That means there is a large area of false positive. False positive. On this side, when the signal is larger than this cutoff, this is CC, what is the LC, decision limit LC, they will go for legal action. And when this is the cutoff, this is the LOD. You can say that this is the signal. And this is also the concentration. With increasing signal, that means there is increasing concentration of your analyte. That means when the signal is above a certain level, we are quite certain that that is present of your analyte. But at the lower signal, the false positive error will be much higher. It may be just due to the blank. Still remember, the most important concept is the signal from the blank and the signal from a sample at near zero or at the LOD, that is the limit of detection. They will overlap, and this is a simple normal distribution. You can't always say that, oh, I am 100% sure that is from the signal, or I am 100% sure that is from the blank. No, there is certain level of false positive and false negative result. So if this is from, we use another color. That is the LOD. So for your this is the signal from your LD from the analyte, okay? This is also a normal distribution. When we say LOQ, LOQ is 10 times the SD. That means the signal is sufficiently large. We are quite certain that the signal is from the analyte and can be accurately be quantified. Okay? From the LQ, that means if this is 3 and this is 3, okay, 9, more or less here. This is the signal from at the LOQ. Sample containing analyte at LOQ. And this is sample containing analyte at LOD. And this is blank. Okay? So phi normal distribution, this will never touch 0. You can't say this is 100%, but the probability of false negative will be very low, okay? You can say that there should not be any false positive because that this is the cutoff at LOD. This is the cutoff at LOD. LOQ, okay? So you can say false positive. Yes, you can, but very low, 0.0 something. Okay. So the signal and the concentration of LOQ will be much higher than that of the LOD, and that will be much higher than the Planck, okay? So here, the concept is most important. Based on approximation, how large or how far, how to set the limit. You can say we can always set a larger factor, then we are more certain to differentiate the signal from the analyte from the background. But we always target at lower reporting limit, no higher sensitivity. So we always set at the marginal case, okay? Because nowadays, all laboratories strive for lower reporting limit. So all the LOD will be just 1% error. That will be good enough. The Planck signal plus 3 times the standard deviation. This will give you back the concentration at LOD. Okay, LOQ is simple, just the Planck signal plus 10 times the standard deviation. That will give you the LOQ. This decision limit just 1.64. 1.64, when you look at the T table, 1.64, 5, that means 10. Where is 1.64? Yes, here. Infinitive. If you carry out infinitive number of measurement of your band, then the error will be 5%. Because one tail, so we look at the 10. So this will give you 1.64, okay? And now, in order to more certain the LOD, so they multiply this 1.64 twice, gives you 3.28. That means double the standard deviation, double the signal to make sure the signal is not from the Planck but from the analyte, okay? So all this K is arbitrary. Different guideline will give you different terms. Sometimes we give you 3, and now it gives you 3.28. And another will give you 4 something. It all depends whether they check the T table or not. It all depends. And whether they want to set the criteria 1%, 5%, or 0.1%. So the K factor will be different. Okay. Now, what about qualitative tests? Will qualitative tests still have a LOD? Yes. Qualitative test means suspected positive or detected. Okay? So it is quite easy to conduct this. Different concentration, you spike to your sample different concentration, and then go through maybe 10 replicate and see the positive and negative result. So here, only at 100 mg per liter, you have 100% heat. So we call this level as the LOD, or the threshold, or the cutoff. Okay? When you repeat more, there may be chances of false negative. But if we repeat 10, all 10 give you the same answer, expected positive result, then that will be set as the threshold. So whether 10 is sufficient or not, once again, it depends on different guidelines. Some guidelines will say that 20 or 30. And now for qualitative test, for HOCRES, I'm just saying HOCRES, that is the only accreditation body in Hong Kong. Of course, you can always apply for overseas accreditation body. We follow one guideline for screening test. One guideline for screening test. And this will be covered in specific requirement, okay? And for that guideline, you need to perform lots of screening tests before you can set out the cutoff. So no matter what discipline, the HOCRES guide will follow that guideline. Yeah, we will cover that later. But the principle is, out of all these check, the level that gives you 100% positive will be the cutoff. Then LQ is simple. That means the smallest concentration that can be quantified with reasonable uncertainty or reliability. That means we are quite certain of the quantified result. And this is the limit of quantification. For limit of detection, we just say that we are capable to differentiate the signal from the background. But the quantified result is really uncertain. In Hong Kong, we do not allow to report anything at LOD. So that will give you the limit of reporting. The limit of reporting is the practical limit of quantification at or above the LOQ. By definition, LOQ is the level that can be quantified with reliable result, with reasonable uncertainty. So the reported results are valid. So we can't report anything below the LOQ. That is the first principle, okay? So you can always set the reporting limit much higher than your LOQ, but not lower than the LOQ. So this is the requirement. So once again, you see similar things as the LOD. It is equal to the K times the standard deviation. So the K normally will be 10. Normally will be 10, okay? Once again, it depends on the discipline and depends on different guidelines. And this is how you determine limit of quantification based on EURECAM. So you see similar flow. The first one is blank, and the second one is low-level sample or reagent blank, and then low-level spike to reagent blank. And the K is you need to calculate the S naught pi first, and then multiply either 10, but you can also multiply by only 5 or 6. Okay, it depends on your intended use. But no matter you multiply by 5, 6, or 10, you need to carry out C. That is the experimental confirmation. You need to quantify to carry out the whole procedure at the level of LOQ to see whether you get back the result, the accurate result with the preset recovery and precision. That is the meaning of reliable result with reasonable uncertainty. Okay? So at the LOQ, or you can say at the LOR, you need to verify by actual spike. That is the C part, experimental confirmation, at least 5 times. Get the meaning? So A and B is how to establish the LOQ, and the C part is experimental confirmation of the established value by spike. Okay? Then we will go to some example, how to calculate IDL, MDL, and how to correct the brand. So maybe let's have the break first, and we will come back at 8:15.
接水或者买水的地方，水。
那里有，你有水？
有。
You can say that this is the concentration or the signal, the level, and this is the band signal, and this is the yeah, it's
x not quite.
no, 11个数，是 band 数，一个是 how to determine the LOD. This is the LOD level. 152. Correct brand, we will talk about this. Yeah, in the actual, yeah, 会讲的。因为有些方法是它是要这样子的风暴阳的数据讲去的，就是 correct。呢個，睇先，即係話。佢係收窄咗，就你呢個成一點五成，C 即係precision 嘅，其實呢個係回應翻上面呢個 CC alpha 即係 precision limit，LC 咧就係你嗰個你可以話 level of compliance 咯，嚟到 level of compliance 咧，咁佢就會攞樣啦，再做睇下係咪真合格。唔係成多一倍，呢個真正嘅 OD， 你呢個 level 嘅 OD 就係呢一個，但係個 LC 咧就係低啲嘅，低啲咧就係話俾官方聽，喂，我而家做咗個樣啊，係有可能有個 analyse 嘅，咁佢咪再抽樣。但你唔會 report 嘅，只不過呢個係 action level 嚟嘅啫，所以係咁先至會用嘅。唔係咪做 confirm？我換咗個方法，你可能冇 confirmation 嘅。總之大過呢個 level 嘅咧，你就要去攞科目版，我哋叫做科目版嘅意思即係會上課㗎，去公司長嘅咁解啊。咁佢可能係科時嚟㗎，不過我哋唔理佢啊。咁真正如果呢個方法嘅 LOD 咧，其實要成啲先至係有多啲信心嘅。呢個咧嗰個 error 好大嘅，呢個 error 細好多咁解啫。因為你個 plan 都有機會大過呢個息率㗎嘛。啊，咁我唔知佢係科真啊。 唔係想確啦，呢個係淨係一個 action level 咋，哎呀，講極都唔明。再攞啲板，然後就拎去俾個 government body 佢哋做，佢哋嗰方面有佢哋自己嘅 LD，咁佢哋就係真係可以上 court 啦。呢個純粹就係 action level 嚇、即係有危機啦，咁所以你要去攞板咁解啫，即係 set 低啲安全嘅保險起見嘅啫。
其实也是问这个，就是为什么 LOD 是 LC 倍？
哇，為什麼你
他说阿尔法等于贝塔，所以它是2倍。我就想，这是不是这样想 ？LOD 就是检测线，LC 是 critical，就是高于它的我就是 positive，低于它的是 negative，是这个意思吗？
那应该怎样说了？这个 LC 高过它就有一个可能它是一个不合格的样品，所以我们要从法律方面考虑。
LC 就是法律的限制。
对，法律的审限，它也有一个可能它是一个 false negative sample 了，false positive
那
sample。
如果它是法律的限制的话，为什么测试的 limitation 会比法律的限制高？
应该怎样说？如果有一个实验所，他做到的是高的这一个 LC， 他就要告诉这个检查执法部门，他要去这个 market 再拿取取样，再交到这个政府的化验所，从事这个法律的程序，可以吗？这个
因为这个图其实 LOD 跟 XLOD 是一个东西，X bar 跟 LOD。
哦，这个是 L， 这个是你的样品里面，如果有一个 L 有一个浓度是LOD， 它的 signal 就是这个面会比这一个 cut off 大一点的。这个是 cut off 的 signal， 这个是 mean signal。
什么叫文档和语音是 LOD？LOD 不是 instrument， 它自己性的。
这是 instrument，LD 是 method 的。
是 method。
对 ，IDL 是 instrument，LD 是method 的。
它是测出来的，不是计划的。
LD 是一个运算来的，只是一个运算，这是based on 你的发阳的 fluctuation， 这个就是一个运算过程来的，知道吗？如果我有一个是，这一个是空白的，它是一个 non-distribution， 这一个是一个样品里面它的浓度是有 LD 的浓度，它也是一个 non-distribution。
如果它是 LOD， LOD 这个 cut off 就是中间是 LOD。
你有問題冇嘅？
因为
有條
它
你沒有
这样子
decision，
如果你是这个 cut off， 有50%，
即係前年即係前年
它是一个 negative sample，
呢個意思。
知道嗎？
都明 CC 用呢個 LC
如果它的
咁就 limit of CC 咯，但係呢個 detection limit 點解會係 CC 我就唔知啦。
这个 LD 是一个 signal， 就是如果有一个样品，它的 signal 大的这个 LD 的 signal， 这个是 signal。
勁多人走咯。
我淨係俾佢話點解聽唔明？點解聽唔明？講咗唔明。
对对对对，
那么这里他们两个 standard deviation 是不一样的。
可以不一样。
然之後後面仲有人喺度笑，
应该比較好一點，
我唔知啊，我話點解聽唔明？
因為它的濃度高一點，它的 signal 比較好一點，所以它的 SD
我揸啲爆啊燒撚
我以为哪一个是阿尔法，哪一个是贝塔？
燒撚笑，
对，
喺度
這一邊是
明估
alpha，
啊，
哪一邊是貝塔
咁啊？自收啦。
那这里也不相等。那如果说assuming 阿尔法 is equal to 这个程序法 ，so LOD is discoverable as
應該這樣做，因為他們兩個也是很接近 zero， 所以他們的 SD 差不多。
低于 X bar 高于 LOD
其實個文字夠長
就
做。
是假一。
覺得
我覺得可能直接要我自己
高於
send
這個
翻成
LD 是
PDF，
假陽。
我都成份 PDF
啊，
先俾
對，這一個是它應該有這個 N 來的，但是它第一個這個 LD 就是假音了。
然后低于 LED 高于 LC。
error property of alpha that is sample is not complete. Complete action is required to set.
这个是这边比较白的，这一边就是假牙，这边是假
佢度，LP 度開始講，開始
我哋諗住咪順便講，
假牙，
其實可以理解。
這個是假煙。
個名嚟㗎嘛，即係後面，跟後邊啊，
LED 是 3C 嘛，那 LQ 就是
OK 嘅，
九个，
但係我
看什么？
不是九个吗？
不是9个，是10个，5个也可以，6个也可以，就是比它大就可以了。
就给它的可以，然
覺得
后
佢呢個係啲 standard 俾嘅
一般来说是
規定
10，
範圍咯。
一般来说是10。
佢呢個話 LQ 係
一般来说
嘅
是
plan 嘅 X
就是这个
加到10
LQ，
個
一般
plan
来
嘅
说是
standard
10，但也可以是5跟
呢度定係呢
6，因
度？
为你可以用这个 experiment 来验证的，知道吗？这个是10，一般来说是10。
見過即係 T 個圖佢都係3、4，
你哋問咗先。
10，即係10佢係用個呢個先10，一全部用高，所以唔知咯，咁張開始睇嘅，而家可以
嗱，其實即係呢個係完全空白嘅，呢個咧就係有少少呢一絲毛嘅，即係佢真係有 N 嚟啦。咁佢兩個嘅 S 其實都係差唔多噶嘛。咁我哋個 cut off 咁計數嘅啫嘛，即係大嗰個食路咧，我哋就話有 M 嚟啦。
我哋都唔知10係幾多。
細過佢咧就冇 M
我哋係背咗，我哋係背
大過
到
佢亦都有個機會
即係
係假
兩
陽
個
性。
係
細個佢亦都有機會係假陰性，其實佢有嘅，咁解咯。咁點解唔係睇呢度 cut 咧？睇呢度 cut 咁咪有50%係假陰性咯，係。你如果你喺呢度做 cut off 嗱，如果你係兩個方 distribution， 你如果喺呢度 cut 即係佢個問題啫嘛。佢話點解唔係喺度 cut？ 如果喺呢度 cut 咁即係話細個佢嘅冚唪唥你都當 negative 咯喎。咁咪即係有50%係假陰性咯，陰性咯 ，negative 咯，你可以 set 呢度㗎，不過你冚唪唥當嘅 negative 啫嘛。咁你 positive 嗰啲你準好多㗎，邊個唔知啫？但係有好多方法你係要越嚟越低啊嘛，我哋要測越低嘅嘢，所以我哋係計到盡嘅通常。咁如果呢個同呢個分別只不過係我用佢一個大啲嘅誤差，我都要用 equal action 啫嘛。其實
我冇叫同先咯，我冇10嗰個即係你嘅，
俾嘅
幾多3
或者如果
所以
即
佢
係話
10
俾我食話喂，你好出去攞版啊，跟住攞科目版，科目版要分開3個嘅。
因為你呢條 curve 你唔會人長頭㗎嘛，你唔會掂到人㗎嘛。
其實係嘅，可能係咯。
俾對家做，佢拎去私人做，另外
你
一個
嗰個99.9%個 percentage 同埋係個 extra 同埋 area
你唔講10個唔夠
佢講10個
所以唔好成日問我，點解
即係講
我成日唔成
LQ 條
同一個方法都得㗎？唔係話呢個咁，
LQ 係個 X 大於
可以告人嘅，呢個純粹係 action 啫，得唔得？
佢只不過將
咁問題呢個佢又
係話 base 係10咯。
即係 action 都得嘅，即係我要攞版，你要攞科目
應該
版。
唔係永強最低個 point 啊！佢呢個你睇下你寫話 X 大過
係啦
X 大過 X
低咗㗎嘛。
面加3X，所以你咪將個3面10個咪就係 LQ。LQ 你嗰個 X 3嗰個3係個 LD 嘅，你將佢10個就當 LQ。X 大過啊嘛，大到呢個你就當佢一回事。咁即係佢 cut off 嘅地方。
咁咪唔告人㗎嘛？
如果唔係點做 LQ？你出數嘅 LQ 係要，即係 LQ 係要去到計到佢咩數。
大鑊啫嘛。咁我咪
LQ 你要夠大啊嘛，你要夠大先可以有信心啊嘛。
呢唔係你好唔好啊？睇下你個，你如果做玩具嗰啲咁，
你講你幾 experience LQ 啊？
你冇需要有個 MC 㗎。假
LQ 我自己就咁。係咯，我 LQ 其實係嗰個 signal to noise ratio 係大過10個先。
即係你話我食咗佢對你個人體即刻有害嗰啲。
你 signal to ratio 個 signal to noise ratio 係3嘅話係 LQ， 10嘅話就 LQ。我唔知，我未見過識唔識咁解釋。
其實我自己整咗貨出嚟嘅，不過咩咁話嘅，
跟住個咩係用
係我話會有個圖嘅，不過即係我哋用啲字咁樣出嚟嗰個真係唔係好清楚好搞㗎嘛。哇！即係因為成嗰啲字，即係數字落去咁先覺得呢個圖出嚟好解啊，就同呢個一樣咯。不過就係呢個咁畫就會清晰啲，得唔得？
都唔
我記得應該畫到咁
大家都明白啊嘛。
LC 跟 LD 之間這一段，
其實我哋
我咪成日我諗下咧，嗰個33339差唔多去
假洋不是假音，是假洋。
明，希望明。
成個同佢
剛才那位同學標的是這裡是
好多有啲原地兜圈。
對。
然後這裡是假牙。
我都唔知我抄嗰啲乜嘢啊，講真。你對聽啲咩嗰陣時決定會抄㗎？我就覺得我呢邊又要抄咩？我諗。
要看你看是 LC 還是看這個 LOD。
唔得醫
如果你是看這個 LC，這一邊全都是假洋，
就是唯一一个，
這一邊就是假音啊，可以嗎？
他沒時間了，他在那個 center，你跑上來
我
嗎？
們方法裡面的最可以檢查出來的值。
是 work range 或者檢測線的，就是 measure 裡面
不是檢測線，是方法的檢測線。
地方它算都是
就是 RBL 的。
他可能心想，我也买的是 PhD，咱也没有分随高随低的。
LD 是 LD 只是我们看到。
No， 这个不是calibration curve， 怎么说呢？你这样两个 mix together， 应该怎样说？应该是一个样品里面，它有一个浓度就是near zero，near zero。
瞓覺啊！
解釋了那個 distribution。
咁如果我嚟寫方案，我可以將
是通過我們的這一個定一個 LOD 的濃
他一個
度，
definition 都要
它就是 near zero 了，你可以可以嗎？
是先有的這個 cut off，再有的 X bar。
成日叫你 compare，佢嗰個 Excel 叫你 compare 咩？
概念是一樣的，概念是一樣的。這個是傳統樣品，這個是陽性的樣品，它兩個也是一個 normal distribution。也可以了。它單個 signal 就是 X bar，但它如果你將這一個做這個 cut off，
我哋最遲嘅9點半。
這一邊全都是假陰性的。
佢啱啱講卡多。
對，就是50%啦。
所以假音是 LOD 跟 LC 之間的 interval，就是那個。
什麼呢？哎，我真的不明白你了，是哪一個 interval？
是 LC 和你的 cut off 之間的
不是
interval。
每一個方法也有 LC 的，一般來說我們不要定這個 LC 的，
LC 一般沒有。
一般沒有的，就只有 LOD。
那如果把它卡住，就是為什麼會是50%呢？
任何樣品，如果它的 signal 是第一個這個 signal 就是陰性，這樣子就是50%是假陰性啦。
就是說我把它無限延長，這邊是假陽，然後這邊就是假陰，是這個意思嗎？
那你可以這樣說。
只跟這個線有關，跟這個線沒關係。就看到不是看是它，然後。
如果這樣。這個是假陽，對，假陽。但是如果你是一個是它的mean signal，有一半它是也是陽性的， 但从这个图看起来，就有50%，你就当它是一个阴色的样品。
OK，但这你的那页说 alpha 等于 beta 等于 0.0，所以说 LC 和 LOD 的位置就是 LD 等于2倍的 LC，那你是怎么回事？
它的就是两个相当接近，应该这样说，它就是这样子。一个是 negative，
啊，
不用 LD、LC， 用 positive and negative， 它就是 positive， 中间
一个是 blank，一个是 type
一个就是 LC， 这个是5%，这一个也是5%，这一个也是5%。
啊，那 LOD 为什么是它们两个大过 LC？
这个是只是，这个是1.64 S band。如果你真的要将它的变成1个百分比，这样子，这个就放大一点，所以也不需要是2倍和3倍，是3也可以的，就是 XB 加3也可以的，但它现在是3.8。
啊，这就是 by definition
不是 by definition， 是这个 standard 说的，不是每一个 standard 也是一样的。我刚才也是说，不是每一个 standard 是3.28，有的是3，有的是4.65，有的是3.14的，所以每一个 standard 不同的，它就是一个 statistic。这一个转 channel， the most difficult part is this limits, because this is a arbitrary estimation, arbitrary, based on statistic, probability of false positive and probability of false negative. Okay, so for this K factor, whether you multiply by 3, multiply by 2, multiply by 1.64, just depends on which guideline you follow. You stick to one guideline. If you follow EuroChem, then LOD will be mean signal plus 3. Okay? But if you follow another guideline, then that will not be 3, but maybe some other factors, because they will not be 1%. They will use maybe 5%, or they will go to the T table to search for the actual T value. So this figure is not a fixed figure. It all depends on the guideline you adopt. So when you want to develop a in-house method, you need to select the guideline suitable for your discipline. If you are general, and without international guideline, then I highly recommend you follow EuroChem, okay? But if you work in environmental testing, sorry, you are forced to follow the APHA or US EPA guideline. That is mostly adopted in Hong Kong, But if you follow if you work in the food industry, oh damn, too many guidelines, okay? It all depends on which area you work in. And for an Hawkers accredited laboratory, there will not be any choice, because there is a supplementary criteria 37 on food testing. They list out all the definition for LOD, LOQ, and the working range. We will cover specific guideline as our next topic after we finish all the MPC, okay? That is the most difficult part, because just by calculation, do we need to verify the LOD or LOQ? This is by calculation. Do we need to add to our sample, our determined level, to see whether we can really detect it, or to see whether we can really quantify it? For EURCHEM, LOQ, you need to have experimental confirmation. Okay, we need to verify. But for LOD, once again, it depends on discipline. For environmental tests, you need to verify. But for other disciplines, we don't verify the LOD. Why don't we bother? We don't report. We don't report any result below the LOQ. So, what is the meaning of verify the LOD? I don't understand. The supplementary criteria are draft based on regional guideline, that is American guideline. They will report result between LOD and LOQ. So this is important to verify the LOD. But in Hong Kong, we don't report LOD and anything between LOD and LOQ. So I don't think this is necessary. But they adopt the guideline and they have put this requirement in the supplementary criteria. We will discuss in detail later. No need to memorize all these magic figures. These are just magic figures, statistic, estimation, okay, based on normal distribution. So, you may ask, do we need to calculate MDL and everything in our examination? In your laboratory report, yes. In the exam, maybe, because I haven't studied. But this is open book. Always remember, this is open book. I will not ask strict, funny or industry. The most commonly just three: food, environmental, and also general. And always make a summary on different disciplines. Then, no matter which discipline, you can get the magic figures. Okay. Okay. Here, just give you some example. IDL, how to determine IDL? Reagent blank, or I should not say reagent blank, I should say calibration blank. Otherwise, it is easy to mix up different terms. Calibration blank. This is only the instrument. The blank will only be the calibration solvent, okay? So 10 replicate of calibration blank. IDL is the average value of blank plus VSD of the blank, okay? Or injection of standard solution. And at the concentration, you have the signals to noise ratio of maybe 3, then that will be the IDL. And lastly, you need to take 6 to 10 calibration curve and then get the intercept. The IDL will be equals to the mean intercept plus V standard deviation of the intercept. The intercept basically is the background. So 3 times the background intercept will give you the IDL, but you need to construct many calibration curve, okay? For most of the case, we don't calculate the concentration. We just get the signal and then divided by the slope, get back the concentration. No need to fit in the calibration curve. If you fit in the calibration curve, that means you have subtracted the intercept. How can you calculate the concentration of the blank? Get the meaning? This is already the blank. If you subtract the intercept, that means you are not getting the signal of the actual background, okay? The concentration of the actual background, okay? That is corrected blank already. So with certain signal divided by the slope, then that will give you the corresponding concentration. So for the signals to noise, what is the signals to noise ratio? It is easy. For most of the instruments nowadays, they have manual, that is built-in function of SM ratio. So if don't think that the background is zero, never. When you amplify, it always happens this way. So the software will calculate the noise level. 5 minutes was you define how many minutes before the target peak, okay? And then they will calculate the signal here. Then the SN will be signal of peak of your analyte over signal, FH signal of noise. Normally, they will use peak height. So when this maximum peak height may be 2, and then if the SN, or this is 5 or 6, then SN will be 6 over 2. Then the signals to noise ratio will be 3. That means this concentration can give you a signals to noise ratio of 3. And this concentration is the IDL, okay? So by series dilution of your standard solution, you can estimate the IDL. This is purely related to the instrument, but not to your method. This, as the IDL is the same for different method, for the same instrument, but the MDL or the LD will be different for different methods, okay? Because the background noise will be quite different. So just using the height to measure the SN ratio, normally. There are built-in function for most of the instruments. They will calculate the SN ratio for you automatically. You don't need to use the ruler and measure the height and then calculate the background noise. No, not in this way. So, when the sensitivity increase, the IDL decrease.
Yeah.
Sensitivity means the slope, okay? So for case 1, if the slope is 1000, case 2, the slope is only 100. It depends on the instrument. This is more sensitive. The background noise is 100. If the IDL is 3 times the SM ratio, that means for this instrument, whenever a signal just can produce 300 signal, then you can differentiate, okay? So the IDL is only 0.3. But in such a case, 300, that means the IDL will be 3 mg per liter, okay? Just by calculation. Noise over the slope will give you the concentration. So this is the sensitivity. So another example is the background noise decrease, your IDL will also be decreased. Assuming the background noise, one is 100, another one is 1000. The slope will be 1000. Signal at IDL n times 3. That means this is 300, this is 3000. then divided by the slope. This will also give you 0.3 and this will give you 3. Okay? So it all depends. Either if you want to decrease, to lower the performance, that means to improve the sensitivities, either you remove the interference, lower the background signal, or you select a more sensitive equipment. That is the choice, okay? So this is basically the same on the backboard. So calibration blank, so the IDL, this side will be, the signal of method blank will always be larger than the calibration blank. And then the solution at the LOD, the signal and the concentration, once again, is always larger than that of the method blank. And at the LOQ point, of course, the signal and the concentration will be the highest, okay? So at such a high concentration, the signal is larger. So you are certainly can quantify the result accurately. That is the concept, okay? Oh, here, just give you some actual data. The IDL, that is the calibration blank, 10 times the mean 41.5, the SD is 15.8. The slope is 1000. So the IDL is the mean 41 plus 5 plus 3 times the SD will give you 82.9. Divided by the slope, then you will get 0.08 mg per liter. In this case, IDL we don't have any blank to correct for IDL. Or maybe it's better to use the Excel. Okay? We use calibration blank. CB is calibration blank. So this is the mean of this 10 data. This is the SD of this 10 data. Then the IDL will be the mean plus 3 times the SD, and then divided by the slope. Okay, that will give you the concentration. Understand? What about the LOD? The LOD is use of pulses blank sample or low level sample. Okay, so it will give you a higher signal from the calibration blank because it contains more interference, more contaminants. So once again, 10 times. So the mean and also the SD. The LOD will be the mean plus 3 times the SD. We are talking about Eurochem, okay? So here, all using the signal divided by the slope will give you back the concentration. The LOQ, also simple, the mean plus 10 times. That means at a sufficiently large signal and a sufficiently high concentration, we can quantify the result. So the IDL will be 0.08, the LOD will be 0.15, the LOQ will be 0.25, okay? How to interpret this data? That means when the signal is larger than 147, the sample is assumed to contain the analyte, okay? The false positive weight is 1%. That means out of 100 determination of the blank, 1 will be falsely determined as a positive because 1%. That means the signal of the blank is larger than get the meaning? Similarly, the false negative weight of the sample solution with analyte at 0.15 mg per liter is also around 1 because the SD is more or less similar, okay? That means when this is the calibration blank, not calibration blank, this is the process blank or matrix blank, okay? So when the signal is larger than, that is the LOD 147, then you will say that the sample is positive. False positive is 1%, okay? Similarly, when I have a sample solution, the concentration at the LOD, that is 0.15, there is also 1% that will give you a false negative result. That means the signal will be lower than 147. That is the case. No matter false positive or false negative, the cutoff is at 147. Okay? Oh, maybe you can say 146 or 147. Okay? So when the signal is larger than 230, you can say that the sample can be quantified accurately. So now I don't need to write LOQ or LOD. Where is here? Then you can understand much better. Not to mix up. Okay. That means here always here so this sample at 0.15 mg per liter. This is the bank, either procedure bank or matrix bank or sample bank or sample with low level, okay? So the mean result, the mean blank will be this is what is the measure figure? Okay, a little bit higher. The mean is 112, 111.2. The mean signal is 111.2. Okay, and now the cutoff. This is the LOD. This will give you 147. And this will give you 230. Okay. Then these two, the SD will be quite similar because both of them are at near zero. This is zero, this is near zero. So the SD, the fluctuation is more or less the same, slightly different. I cannot say exactly the same, but much more. So the false positive here is 1%. The false negative is also 1%. And it is easier to understand. This is false positive. This is false negative. Okay? And now also calculate the second example is blank correction. So up to here, when graphically plotted, it is easier to understand. So the x-axis here is the signal and also concentration. This is the signal, increasing signal, and this is increasing concentration. So here the concentration is 1.15. Here the concentration is 0. Here the concentration will be at the 0.25, 0.23. Okay? That means at 0.15, it should give a signal also in normal distribution. The mean signal will be much larger than that at 147, okay? But if we set the LO, the cutoff at this signal, then 50% will be false negative. Understand now? So here, the second example is blank correction. What is the meaning of blank correction? This is specified in the test standard. The equation, the concentration is equals to, maybe, I don't want concentration. A, the analyte, is equal to the signal of sample minus signal of your blank. And then, I may not be safe. This is concentration, okay? And then, times volume over weight. And that will be blank correction. For some of the discipline, they do not correct for the blank. This is blank correction. If don't correct just directly, read out from the calibration curve, we will control the blank, set criteria for the blank, but we don't correct for the blank. So two different approach. We don't correct the blank, but we just set requirement on the blank. Okay?
Calibration curve using blank correction.
So understand first what is blank correction. Okay? Now, if we have blank correction, what should we do? If we analyze the sample for once and we just analyze the blank for once, okay? The blank meaning procedure blank. Should be the procedure blank, okay? So procedure blank, I just use or I use the data from above. Okay, I just use the data from above, okay? And this is your sample or low-level spike. I can't use procedure bank. Why? You must use low-level spike, otherwise you can't determine the LOD. If this is procedure bank and this is also procedure bank, you will cancel everything. So, in this case, if blank correction case, you must use a blank that is the procedure blank, and then use a sample low-level spike to create some signal, okay? then the result should be corrected. So the low level spike signal minus the blank signal. You have, that means we will prepare one low level spike and one procedure bank. One spike, one bang, one spike, one bang. Then the first one minus the first bang, the second one minus the second bang. Okay? So we have 10 results. We have 10 results. The mean and then the SD. Okay? Now, the calculation is a little bit different. We also have this loop here. And we have the S 16.6. The S naught will be the S times square root 1 over n plus 1 over nb. Okay? Now the n is 1. 1 over nb is also 1. That means this is 2. The S naught will be the n. This is the n 226. The S over the slope times square root 1 over 1 plus 1 over 1. That is square root 2. Okay? So that will give you 0.0235. Okay? And then the LOQ will be just the S naught multiplied by 3. And the LOQ will be the S naught multiplied by 10. Why is that we don't consider the mean? In this case, the mean is not the mean signal of the blank. This is the mean signal of the low level spike. So we don't count that. This is actually due to analyte. Our objective of determination of the LOD is the fluctuation above the background. Okay? And in this case, we don't have background. The background is 0 already. We have corrected it already. So we just consider the standard deviation. Okay? Just like this scenario. Still remember the LOD, the figures. The EuroChem also have this 0 plus 0 plus 3 S naught. You have corrected it. So the blank will be 0. The mean will be 0. Okay? So by putting some figures, you will understand what is the meaning of corrected band and how to calculate. The n is only 1 because we carry out only one band each time, only one low level spike. If 2, then this will be 1 over 2 plus 1 over 2. Then the standard deviation will be much more certain, and the LOD and LQ will be lower. Because you measure twice, the mean results are much more certain. The band results are also much more certain. The overall result, the standard deviation will be reduced. Get the meaning here with band correction. So there is 2 terms, the S or the S naught and the S naught pi, okay, as given in EuroChem. It's based on the method. If your method don't correct blank, this part can be totally ignored. If the method specifies that you need to carry out blank, and one time some method will say that you need to determine the blank for choice, then NB will be equal to 2. And the sample solution may be only once. So they may not be exactly the same. It all depends on the situation, okay? But this is the way
คือ
how we
standardization ของ
determine the LOD.
咁你
If there is
想
blank
講
correction.
standardization of 個 condition，我哋最尾想有講最
Any questions here before we move on?
係 standardization，咁大家可以注意到我哋最尾想要嘅係 condition 呢？
我明白，但係點解可以用 standardization 全部都係講清楚？
No? Then we move on
我
to
大概明你意思。
almost the last topic. I cannot say the last
雖然係
of the MPC. Recovery and precision. Recovery and precision.
你將現成啲現實世界
So,
容易啲想像到。
Regarding recovery, there are quite a number of different terms. Trueness, accuracy. Trueness is how close the average value obtained from the infinitive number of replicate measurement and the reference value. Okay? That is trueness. And accuracy is how close the agreement between a measured quantified value and a true quantified value. So basically, trueness and accuracy, just the same meaning. How close to a true value or a true reference value. So when we say trueness study, what is the meaning trueness study? There is a reference value. Normally, when we say trueness, we will make use of CRM. We compare our result with the reference value as given on the certificate. Okay, that is trueness study. Another trueness study is comparison of your result with another accredited and validated method. That is also a trueness study. Either comparison with CRM or comparison with the another method. Okay? Bias. Bias is basically trueness plus bias is equals to the reference value. That is how close. Accuracy and trueness is how close to the reference value. Bias is the difference or the systematic error. You can't get the reference value. Why? Because your method is not good enough. That is systematic error. Okay? So, the difference between the expectation of the test result and an accepted reference value. Bias may not be negative. We always say that, yes, oh, our recovery is not good enough, it should be negative. Somehow, bias can be a positive bias. So the total bias is method bias plus the laboratory bias. Method bias plus the laboratory bias. That is total bias. You may still remember when I talk about CRM. When I talk about CRM, there are some certificate having A, B, C row. The certified value are quite different. Now, this is a good example to explain total bias. So, a CRM, that A, for example, 200 plus or minus 4, okay? A is the true value. This 200 is the amount by balance we add to the matrix. So this is the true value. We know the sample weight. So this is the gravimetric method. You add it, this is the true value. B is the you can say method bias. We get 180, 10, okay? C is the acceptable range. Acceptable range may be 175 plus or minus 20, okay? That is 155 to 195. So here, for a specific method, even for the RMP, out of 200, they just get back 180 by specific method. That means the method itself, that is by B is specific method. The method bias is around 20, okay? And here, the C is interlaboratory. The mean result, the true reference result, or the interlaboratory mean, is 175, okay? So when I plot the graph, 200 and then 175 is the true reference value, and then this is the method bias. This is the method bias. When if you report a result, one laboratory result, 190. That means your result is somewhere here. That is your laboratory bias. So this time the total bias is equal to the method bias, okay? It's 25. And the your laboratory bias is 20. It's 20. It's 20 only. Okay? But if another laboratory, they report a result, $160. So this laboratory bias will be 15. The method bias is 25. The total bias will be 40. Okay? Will be 40. Then in this case, it is easier to understand. Because for the first scenario, don't think that with a specific method, that means if within a interlaboratory study, you specify a method, that method may not be 100% recovery. Then by the best performance within that laboratory, the mean result is only 175. So, but we know that we have add 200 into our sample. So you just can recover 80% of the analyte in the sample. So the method itself have bias from the true value. The true reference value and the true value have a bias of 25 unit, okay? And the result obtained by your laboratory is the difference between the inter-laboratory result or the reference result from your own result. That is your laboratory bias. That means there are two bias, okay? The two add up together will give you the total bias, okay? So the true value, just the same, 100 nanogram. The mean result of many laboratory true reference value of the same method is 95 nanogram. Result of laboratory 89 nanogram. Method bias 5 nanogram. Laboratory bias from true reference value is 6. Total bias will be 11 nanogram. Okay, just the same meaning, but I use other figures. Okay. So this is the bias. For some of the method bias is quite quick, you can say. When we say we added 200 and we can get back only 175, that should be a rational method. Otherwise, if this is an leachable or soluble method, basically there is no true value. The added amount is meaningless, okay? So the method bias is 0 for that case, because that will be point to the reference, the traceability is to the method, okay? For this, we have a true value because this is a rational method. Getting the total, we try to get the total, but based on the method, we can't get the total. So recovery, the extraction efficiency of an analytical process reported as a percentage of the known amount of analyte carried through the sample extraction and processing. This is quite easy, you can say that. What is the meaning? I say that it is quite easy. This is the amount in your 45 sample. 45 means spike, also means added. That means we know the amount of analyte added to the sample. And this is the unfortified sample. And Ca is the amount you added, okay? Times 100% will give you the recovery. For CRM, when we want to assess the trueness, recovery will be your observed value over the certified value, and that will give you the percentage recovery. Or basically, this turn into simplify this equation, observe minus the matrix over the amount of spike. The closer out to 1, that means the smallest the bias. That means the recovery is approaching to 100%, okay? It gives you the extraction efficiency. Now, what is suggested within the EURChem guide? Measure RM using candidate method for 10 times. That is the second month. That means comparison with another method, okay? Oh, measure RM, no. That means you carry out the CRM for 10 times and carry out the recovery. And then this is the measure matrix blank or test sample unspike and spike. The second approach is spike recovery. The first approach is CRM, okay? When we say CRM, that means this is the matrix CRM. Matrix CRM. For SPI, of course, we SPI reference material or standard solution made from certified CRM, that is acceptable. The first one is matrix CRM. Otherwise, there is no use of study the trueness. The certified value is the amount of analyte in the particular matrix you want to determine. For example, soil, sludge, food, fish, anything, okay? That will be matrix CRM. The third approach is measure the CRM or SPI using alternative method. Normally, we will not carry out the C part. If you have one method already, why don't bother to prepare another method, okay? So for qualitative test, we will determine, we don't have recovery qualitative test, but we will determine the false positive and false negative percentage. So the total non-negative and then the false positive times 100% will give you the false positive. And then another way round. So, recovery, trueness, and bias. Is it possible to have recovery larger than 1? Due to uncertainty, yes, there may be, yes. And we have reason the recovery is larger than 1. The first one is large background interference. Why is that? If we have large background interference, then we have recovery larger than 1. We mistaken the signal from the interference as signal of your analyte. Then the signal will be overestimated, and then the amount of analyte determined will be higher, and the recovery will be larger. Okay, and the second case is difference in recovery of surrogate and that of the analyte. For using internal standardization, somehow it is quite common the recovery is larger than 100, okay? Due to fluctuation in signal, due to fluctuation in your internal standard or surrogate, especially surrogate. Now here I give you an example. If the recovery of surrogate is only 60%, that means the performance is not exactly the same. And the recovery of the analyte is 70%. That means assume we have 3 nanogram of surrogate and 3 nanogram of analyte in sample. Signal of 3 nanogram of analyte is 30. Signal of 3 nanogram of surrogate is 40. After extraction, that means we just get back 1.8 nanogram of the surrogate. Then the signal will be 24, just WASO, okay? And analyte is 70%, so we get back 2.1 nanogram. The signal is 21. Here, the WASO will be 0.875, okay? Okay, so we use the calibration curve for food. Just use any, we have the calibration curve here. We use this calibration curve. Here, we use this calibration curve. WASO minus the intercept over slope, okay? So here WASO minus intercept over the slope, you get back 3.576 nanogram. But we have only 3. So the recovery will be around 120 because the WASO have changed. Original, the WASO should be 3 to 3 is the signal is 30 to 40. Then the ratio is 0.75. But now you have changed to 0.875. Okay. No, it is better to add the original ratio is 0.75. Yeah. Is equals to 30 over 40 equal to 0.75. And now because of difference in the extraction efficiency, the ratio becomes 0.875. So you have overestimated the concentration of your analyte, okay? So it do happen for multi-element. For multi-element, if we use only one surrogate for 4 to 5 analyte, somehow the performance cannot be exactly the same for all the 5. Some will be more close, some will be higher, some will be lower. Then constantly, this is a systematic bias. Constantly, recovery of one analyte will be lower. Constantly, recovery of another analyte will always be higher than 100, okay? So for multi-analyte analysis, it do happen in such a case. This is due to difference in recovery. So this is why the recovery can be larger than 1. So if I say that, oh, recovery can never be larger than 1, true or false? In principle, it should be true. But actual case, it can be false due to these 2 reasons. Another reason is uncertainty. But just right down here, okay? So for 100% marks, you can give me example, demonstrate with example, okay? That will give full marks. So another one, recovery surrogate is 70, analyze 60, then just the reverse. After extraction, the ratio will only be 0.645. The result will then be 2.58. And then the recovery will be 80 something, okay? 86.5, okay? So the result will be estimate or underestimate. But no matter which is overestimate or which is underestimate, you can still see that the quantified result is 2.59. If the recovery is only 60, then you can just get back 2.4. If you don't use the surrogate. Get the meaning? If you don't correct the recovery by surrogate, your result will even be worse, okay? You can't get the actual amount. And the case, 60% don't think that it is not good recovery. It all depends on the concentration. It depends on the complication of your extraction process. Okay. For some of the requirement, the acceptance criteria of recovery can be as low as 40%. 40%. 40% is acceptable, good enough already. So don't think that, oh, now the recovery is 80 something, it is so bad. No, it is quite good already. Okay, we will stop here and we will continue. Oh, no, stop first. I don't left. How many here are there? Let me see. Oh, have all of you signed the attendance? Okay. So, Anybody of you here first have problem to sit in the examination 1 week later?
那这什么英国啊？不会蠢的。
That means the original last date for this course is 15th of April. But we can defer the examination to the week 20. Any day of 20, okay? So I think this will do good for you. But thinking that some of you may hurry back to hometown. So anybody here have problem? At least here? No? Which day do you prefer? 2021 or 23? 22? 啊？嗱，你哋諗啊，如果係擺到 last day 咧，你哋係遲啲放假咁解嘅啫。
我又唔要佢啊！
20, 21, 22 20嘅大佬個禮拜先放假。
Oh, you have presentation on 24, okay? So, which day do you prefer?
最多咪請年假。
20 or 21 or 22? Oh, okay. Last minute, that means then I will fix to 22. I will send an email asking all of you to confirm that there is no problem because some of you are not here, okay? So next week I will confirm with you the examination day and hopefully the laboratory day. Yeah, I still need to seek the advice from Dr. Chen, see whether which day is available for us to do the laboratory work, okay?